Okay, this is going to be the second video on using the Lagrange remainder to find how accurate your estimate was for a Taylor polynomial. Now, if you haven't done it yet, I would watch the first video because, first of all, we described where this Lagrange form of the remainder came from. And then at the end of that video, I suggested that if you follow these 3 steps, they make a pretty good guideline for solving these problems. Now, in the last video, we didn't solve a specific problem, just went through where the rule came from. But in this video, let's actually go ahead and we'll solve our first one, and the first problem is going to look like this. So we'll work with a trig problem on this one, and suppose it read like this. Use a 4th degree Maclaurin polynomial to approximate the cosine of 0.3. And then a couple of other parts, we want to estimate the maximum possible error using the Lagrange form of the remainder. And then finally, we want to give a range of possible values for the final answer. So the idea is this. We'll start by finding a 4th degree Maclaurin polynomial. Now remember, if it's a Maclaurin polynomial, that means it's centered at 0, so c will be equal to 0, and we want this. And we'll use our steps. So let's take one quick look at the steps. And again, the steps look like this. They look pretty intimidating at first, but really, as we go through it, I think you'll see that they're really each step of this process is really pretty straightforward. Now here they're all bunched together. When we actually do the work, I think we'll do this. We're just going to spread them out, and it will be the same steps but in a spread out form, and they'll look kind of like this. So as I scroll down here just a little bit, it's exactly the same steps, just spread out where we can actually show the work in between. So we'll go back up to the start and we'll kind of run through these and just check them off as we go through. So what the first step of the process says is this, is you want to evaluate a Taylor polynomial for whatever degree you choose to get an initial approximation. So some things that we know here are this. We'll go ahead and write these down as we go. F of x in our problem, f of x is equal to the cosine of x. And specifically, we want to find the cosine of 0.3. So to start with, you have to do this. You change the cosine of x into a polynomial approximation. So I'll go over here and I'll have something that looks like this. I'll have the cosine of x, and to get its polynomial approximation, most of these you should have memorized. Let's go back and take a quick look. For common functions, earlier in the course, you should have run across this, power series for some common functions. And you had things like the sine of x, the cosine of x, e to the x, natural log of x, and so on. Well, what we're interested in is the cosine of x. And we want a 4th degree polynomial. So here's the expanded form of it. We want a 4th degree polynomial, so we'll just select the first 3 terms of this to represent the cosine of x. Now again, if it goes off to infinity, then the cosine of x would be equal to this. Once you cut it off at a certain fixed number of terms, then the cosine is approximately equal to this. So just remember, the cosine, we've got 1 minus x squared divided by 2 factorial plus x to the 4th divided by 4 factorial. And that's what we'll start with. So look that up in your tables, go back to the book, and you can actually go ahead and write that down. So this is going to be 1, then you're going to have minus, actually. We'll go ahead and change that to a minus. 1 minus x squared divided by 2 factorial. Then you'll have plus x to the 4th divided by 4 factorial. Now one difference here is this, and actually I wrote that down wrong. Once I limit the number of terms, rather than being exact anymore, this is now going to be, the cosine is approximately equal to this. Now in our problem we had this. We want to evaluate it when x is equal to 3, so this would be x right here. So I know that x is equal to 3, and I also know, since it's centered at 0, that c is going to be equal to 0. So you might keep these 2 things in mind as you begin to fill in this stuff down here. Okay, first step is to do this. You want to evaluate this Taylor approximation. So I'll go the cosine of 0.3 is approximately equal to 1 minus, and in place of x, put a 0.3. So I've got 0.3 squared divided by 2 factorial. Then plus, and again, in place of x, put a 0.3 to the 4th divided by 4 factorial. And when you evaluate this, you will come up with this. It'll be 0.955338. 338. And what this is going to be the fourth order or fourth degree polynomial approximation of the cosine. So we'll put a little box around just this thing right here. So that is your approximation. Now, if that was all you were interested in, you'd be done. But what you want to know is this is an estimate of the cosine. So this thing is approximately equal to the cosine of 0.3. But now the question is, how accurate an estimate is it? So that's the first step done. So we got step number one. We'll put a little check mark over here. We're finished with that one. So now to figure out what the remainder is, let's scoot things down here a little bit. Now you're going to go to the Lagrange form of the remainder, which looks like this. Now again, if you're not familiar with this, watch the first video and it will explain where it all comes from. Now what I would do is this. A couple things, and you got actually three parts to this. This, and this. Now, two of the parts you know, so let's go ahead and we'll just write those down. What I've got here is, here's an absolute value of the whole thing. And then I think I'll go ahead and put this bar in here, which looks like this. Now, the way it works is this, and I think I'll change to red here where you can see this. We've got a fourth degree polynomial, so in this case, n is equal to 4. Now, what the Lagrange form of the remainder says is that you can estimate the remainder by using the n plus 1 term. So in our problem, it would look like this. If n is equal to 4, then n plus 1, 4 plus 1, this would become 5 factorial. We've got x minus c. This n plus 1 would become 5. And you want the next derivative. This would become f, the fifth derivative of this thing. So what we're going to actually estimate would be this. We're going to have a 5 factorial right here. We will have, in place of x is, should be a 0.3, sorry, 0.3 up here. This should be a 0.3 minus 0. Raised to the fifth power. And then in here, we're going to have, we want, and I think I'll write it like this, f, the fifth derivative of x. And I need the absolute value of that. So later I'll have to estimate, and what it says here is estimate the maximum value of this thing. So it looks like this. So you know this, this part's pretty easy. The next step is this, is you're going to need the fifth derivative. So that brings you to the next step in the process. So since you need the fifth derivative, the next thing is to find the n plus 1 derivative, which is the fifth derivative. So to do that, it's just a matter of patience on this thing. So you started, your initial function was f of x is equal to the cosine of x. So just run through all your derivatives until you get this. So the first derivative, the derivative of the cosine, is the negative of the sine. Then you want the second derivative. So the second derivative, and again, it'd be the negative of the sine, which would give you the negative of the cosine. Then the third derivative would give you the negative of the cosine, but the derivative of the cosine is the negative of the sine, so you'd have the negative of the negative, which would turn back into the positive of the sine. Then you go to the fourth derivative, and the derivative of the sine is the cosine. And finally, we get around to the one that we're interested in, the fifth derivative. And the fifth derivative, the derivative of the cosine, is the negative of the sine. And we'll put a little box around this one. So you needed to determine and find the fifth derivative. So what that means is you can now take this and move it back up here. So I'll switch this out, and in place of the fifth derivative, I'll write down what it actually is. So that fifth derivative is the negative of the sine of x. So it looks like that. Okay, so now the next step is this. And again, this whole thing is in a set of absolute values right here. So you've got it down to this. Now, the next step is this. You know this part, you know this part. This part, the best you can do on this, and that's what this next step says here. You want to estimate, so we'll estimate the maximum possible value of this. Possible value. And again, you're not interested in getting it exactly. You just want to know what is an estimate of the maximum possible value of this thing. So let's scoot down and try that. So what I've got is I know that the fifth derivative is the negative of the sine of x. We'll scoot down to here. So I got the fifth derivative of x, and I know that's equal to the negative of the sine of x. And according to the rule, I want to get that, but actually I just want to know the absolute value of it, regardless of whether it's positive or negative. I just want to know what's the maximum it could be, so we'll put some absolute value signs around that. Now, this is the step that generally in this process causes students the most confusion, but it should actually, in a way, be kind of the easiest. Now, the idea is, I want to emphasize this here. You don't want to make it just an estimate. Make a reasonable estimate of what the maximum value is. And a good way of doing this, I've always found, is if you can sketch a quick graph of it. Off that graph, you can get a really good idea of what the maximum would be. So let's go ahead and do that. So what I want to do is just to sketch a graph of the negative of the sine of x, and I'll do it fairly quickly here. So I'll start with this, and we'll go down like this, and then I'll come across here and go over to here. Now again, I'll go out to about, I think I'll go out to about 2 pi here. And again, just something quick. Now, a sine graph would look like this. It would go up, down, up again. If it's the negative, it just flips it upside down. So if you flipped it upside down, this graph would actually look something like this. It's going to go from here to here, over to here, and so on. So that's a graph of the negative of the sine of x. Now, what you've got is a range. Let's go ahead and put this here. You want to find it in the range c is equal to 0 and x is equal to 0.3. So it should be somewhere on this interval. So I think we'll put this in blue. So again, if this is pi right here, then this is 0. 0.3 would be, say, about, we'll just roughly say it's about right there. There's about 0.3. So what you want to know is what is the maximum value of this graph, and I'll draw you a picture of it right here. That's actually going to be the maximum value. But the question is, what is it? Now again, you can get a rough estimate on these things. So just for any cosine or sine graph, the lowest it ever goes is a -1. The highest it ever goes is a +1. So the range on this thing, it's going to go somewhere between a -1 and a +1. It's got to stay in there. So, and this is where it's a little uncomfortable for a lot of students because they want to get this as accurate as you can. But you could actually make the argument that the biggest this thing could ever be is between plus or minus 1. So I'm going to say that the maximum value of this thing, so the maximum estimated value of this thing right here is 1. Now again, just looking at it, it looks like you might go down to a -1, but again, if you want to say that that distance right there, the biggest it could ever be would be a -1, that's okay. But remember, you're going to take the absolute value of it, so it's going to wind up just being a 1 anyway. So that's going to be what you get for the estimated maximum value. Now, before we go on, this is actually worth taking a little bit of time to explain. A lot of my students do this. They are very uncomfortable with this 1. They look at it and they say, well, aren't you being a little bit loose on that approximation? Couldn't you do better than that? And my own students will come up with arguments that look like this. They'll say, well, if you took the tangent line right here, and suppose that tangent line came through like that, it goes through at a 45-degree angle. So if you did that, and let's suppose that if this distance was 0.3 here, and this is a 45-degree line, you could make the argument that this distance right here is also 0.3. So you might, and you can argue very convincingly, that the maximum value of this black line has to be less than 0.3, so you could argue that the estimated maximum value could be 0.3 instead of 1. And that's just fine. If you wanted to go through that much accuracy, that's fine. But it will surprise you how loose you can be on some of these estimates and still get a reasonable answer. And I like to think of it like this. I'm going to go ahead and put a little slide up here where you can see it. But one of the most important things to remember when you're working with Lagrange estimates of the remainder and polynomial approximations is this. If you keep this in the back of your mind, I like to say, rather than stressing about trying to get exactly, just relax. It's only an approximation. If you can remind yourself of that, you'll be okay. The idea is if you're using this thing, suppose you're out in the field somewhere working on these things, is all you need is a rough approximation of the cosine of 0.3. So you don't really have to go through a lot of stress on trying to figure out whether it's, if you use 1, you're going to get a great error approximation. If you use 0.3, you'll get an error approximation that'll be a little bit better. But in general, as you'll see graphically when we look at this, there's not a lot of difference between these two. And you'll see that it's almost insignificant. So again, I would emphasize, when you're doing this step, all you need is a reasonable estimate of the maximum possible value. And I'll emphasize again, don't worry too much about it. Relax. It's only an approximation. So you can be a lot looser on your approximation than what you maybe have done with work in the past. So we're just going to go with a 1 here. Okay, so with all that, now let's go down to the next step. What the next step is going to be is this. So we finished, we got our derivative, we made a reasonable approximation of the answer. Now we need to find is just to evaluate this expression. So let's go back and we'll plug the things that we know in. So what I've got is, here's the absolute value. Here's the bar on this thing. Goes over like this. Now, I estimated the maximum value of the fifth derivative, and I got 1. So I can put a 1 in right there. This was, and again, we can kind of look back up here, n plus 1 is 5 factorial, and x minus c to this is 0.3 to the fifth. So we'll plug those two in. So if we go down here, this is going to be 5 factorial, and this would just be 0.3 minus 0, which would be 0.3 to the fifth power. And it's the absolute value of this whole thing. So what that's going to give you, if you run through it, it'll be 0.000020. And what this is going to be the maximum possible error. So it could be off by plus or minus that amount right there. So now you know the maximum possible error. So you found the approximation, you found the possible error. Now the next step is to figure out the range that this thing falls in. So let's take a look at that. Now what that's going to be, and we'll sort of write it down like this. You're going to have some f of x, and f of x is going to be less than or equal to your polynomial approximation, and then plus the maximum error, and it's got to be greater than or equal to the polynomial approximation minus the maximum error. So you can write it like that. Okay, now to fill these in specifically, what we had was this. Our f of x was the cosine of x. And in this case, it was actually the cosine of 0.3. And we did a fourth degree polynomial approximation, and we came up with, we'll go up here and take a look at it, we came up with 0.955338. So we'll put that in back down here. This would be 0.955338, and this one would also be 0.955338. Then to this, you're going to add and subtract the remainder, which was 0.00. So this will be 0.000020, and this is going to be 0.000020. So from your estimate, you add the maximum error and you subtract the maximum error. So what this will give you would be this, your estimate of the cosine of 0.3, and if you added these two together, you would get 0.955358, and on this side you would get 0.955318. Now actually I'll put a little box around these because this actually is the answer. I think I'll do it in red here. So if you draw a box around, this gives you the range of the accuracy of the answer. So we'll go over like this. Now, one final thing, if you actually did it on a calculator, you would come out with the cosine of 0.3 to 6 decimals on a calculator is actually 0.955336. So sure enough, you say that your estimate of the cosine of 0.3 is going to be between this number and this number, and sure enough, it actually is. So that's the answer to the problem. You made an estimate of, on this part right here, here's your polynomial approximation of what it would be, and then plus or minus this error, and it falls in this range. Now, at this point, you would actually be finished with the problem, and you're done, but I think it helps to show graphically what this looks like and how accurate it is, and it'll also show why in this step up here, again, you can be pretty loose on this, and you'll see why here in just a second. It's going to surprise you visually when you finally see it how accurate the answer is. So let's do this. We'll leave it right here. Now what I'm going to do is just put a graph of this thing up here, and we'll look at each part. So it looks like this. Now what the blue graph is, this is the exact value of the cosine, so that's a cosine graph. What the red graph is, that's the fourth order or fourth degree approximation. And again, the fourth degree approximation, actually, if you look up in this area, does a pretty good job. So the closer the red graph is to the blue graph, the better the approximation. Now specifically, we're going to look at this point right here, is we wanted it when x is equal to 0.3, and that's where this little light blue dot is right here. So what we'll do, let's go ahead and just zoom in around that dot and see what this thing actually looks like. So all I'm going to do is get in closer. Now, at first they'll look the same. If I begin to zoom in on just this point, we'll get in close, and at first it looks like there's just a single line there, but there's actually two lines, and if you get in close enough, eventually that red line will begin to separate from the blue line. So what I'm going to do is I'll kind of scroll down here a little bit, just keep zooming in, and keep zooming in, keep zooming in. Again, at first it looks like there's just a single line, but all that means is you've got a pretty good approximation. So let's keep going in, and if you keep going in, at some point that red line and the blue line are going to begin to separate. And we keep zooming in, keep zooming in. And again, this is a very accurate approximation. Keep zooming in, keep zooming in. Keep zooming in, and finally you can begin to see some separation between the red line and the blue line. Now remember, the red line is your approximation. The blue line would be the exact answer. So if we get in here somewhere, eventually they begin to separate. Now to see what each one of these things are, let's do this. If you look down in the right-hand corner down here, right in this area, this will actually give you the values of the points. So graphically, let's see what we've got here. Now, if I hover over this blue dot right here, look in the lower left-hand corner, and it says 0.955338. And what that is this thing right here. So my approximation was 0.955338. That's this blue dot right here. Now, the exact value was 0.955336. That's this blue. So if I hover over the blue one, now look in the lower left-hand corner, and sure enough, you get 0.955336. So that's the exact answer. Here's my approximate answer. But what I want to know is, how accurate was I? Suppose you didn't know this. I'm going to go ahead and turn this blue graph off. So suppose you did your approximation and this is all you had. Now let's do this. Let's back off just a little bit. Say to somewhere about right in here, and I'm going to go ahead and put the limits on. So what happens is I've got a line that goes through this is the upper limit, this would be the lower limit, and we'll put two black lines to represent the upper and lower limit of this range. So let's go ahead and stick those on there. So I'll do it like this. Now, I'm going to still turn off that blue graph just for a second, so it looks like this. So we'll zoom in just a little bit more. Now again, the blue dot is the 0.9558. The distance between this blue dot and the top black line is the positive 0.0002. This part is the negative, and all you're saying is that the actual value of the cosine has to fall somewhere in between those two black lines. And if you zoom in a little closer here, we'll get in where we can still see the thing. If I go ahead and then draw that blue line back in there, you'll see that sure enough, the blue line does fall inside the two black lines. So you've got the range of the estimate. Now at this point, it looks like, you might look at this and say, well, that looks like a pretty bad estimate. It seems like a pretty wide range, but you can't appreciate how accurate it is until you zoom back out again. So let's zoom back out, and this is why, again, I go to that thing, don't worry too much about your estimate, because by the time you zoom out, you'll see that these two black lines become almost insignificant. So let's just start here and start zooming out. So as we begin to zoom away, Now, initially, the blue line seems to collapse back into the red line again, but as you get farther and farther away, notice the distance between the two black lines is getting smaller and smaller. If you get far enough out, it looks like you can't even see that difference anymore. You continue to get far out, it looks like it's a single line. Now notice, what looked like a huge gap between those two lines is almost insignificant, it's so small. You keep going back out, and eventually you can tell that what you got there was an extremely accurate estimate just using two terms. And again, just a reminder, there is still a range in here, so we'll do one last thing. Let's zoom back in one more time and watch them as they expand again. So we'll go in, and at some point, the red line and the blue line begin to separate, and at some point, that single black line will separate into an upper and lower range, and your answer is right in there somewhere. So that's kind of what the whole process looked like. And the idea, when you find the range, you're getting the plus and the minus on the black line. But I'll close with a couple things here. Let's go back to this. One of the things I want to emphasize is as you work with Lagrange approximations, it's a good idea if you just keep this in mind. Relax, it's only an approximation. If you were looking for a more accurate answer, rather than messing around with the term where you estimated the derivative, the best way to improve the accuracy of the answer is just add another term to the original polynomial. Rather than working with a 4th degree polynomial, work with a 6th degree polynomial, and that will have much more an effect than this is. So again, don't worry too much about estimating the maximum value of the derivative. And then finally, the last thing is, if you go back to these original steps again, and if you use these steps to guide you through, they'll usually do a pretty good job. So that's the first example, and that one used a trig function. Now in the next video, we'll do the same thing, but we'll evaluate something that uses e to the x and show you what the differences are on that. But again, follow these steps, and they'll generally do a pretty good job of getting you through these problems.